First problem, moving a box. A 230 Newton force is applied to a 46 kilogram box that is initially at rest and located on a flat horizontal surface. The coefficient of friction between the box and the surface is 0.30. So there's friction down here. Draw a free body diagram for the box, find the acceleration, then how far will the box go in 15 seconds? What will be the velocity of the box after 15 seconds? And finally, find the kinetic energy of the box at 15 seconds. A couple of more parts of the question. How much work is done on the box during the first 15 seconds by the applied force, the friction force, the normal force, gravitational force, and net force? Compare the work done by the net force and the final kinetic energy. First, draw a free body diagram for the box. The box is pushed forward by the applied force, so it is drawn to the right. Notice it comes out of the box. Even though you're pushing it from the left side, all vectors, all force vectors should start on the actual object. So it's pushing it to the right, so it starts at the center and goes to the right. Because there is a coefficient of friction between the box and the surface, a friction force, which we label F sub Fr, is present. It opposes motion, so it is drawn to the left. The gravitational force points down, and the normal force is the surface pushing up on the box. Find the acceleration of the box. So that means we need Newton's second law. We'll separate our forces and the acceleration into the x direction, horizontal, and the y direction, which is vertical. Let's look at the x direction first. The sum of the forces is ma. What forces do we have? We have F applied, which is to the right, which we generally take as positive. We have the friction force to the left, which is negative. The acceleration is to the right, so it is positive. Now let's look at the forces in the y direction. We have the sum of the forces is ma, Newton's second law. We have the normal up, so it's positive, mg down, so it's negative. And the acceleration, well, the acceleration is going to be 0 because the box is not bouncing up and down. So we have normal minus mg is equal to 0. We now have two useful equations derived from the free body diagram. We have the x direction equation right here and the y direction equation right here. Why do we have a y direction? Well, we're going to use that to find the normal force, which can then be used to calculate the friction force. The general form for friction is force of friction is the coefficient of friction, in this case kinetic friction because it's moving or sliding. It's mu k times Fn, so we can substitute mu k Fn, the normal force, for friction. So here's what we got for the free body diagram, and then we replace the force of friction with mu k normal force. We also know that the normal force minus mg is equal to 0, so the normal force is just mg. We then substitute that in for the normal force, and we wind up with the applied force minus the coefficient of friction times mg is equal to ma. Now we can solve our x direction force for acceleration and substitute in the numerical values. So here's our equation from the previous slide. And what do we do here? We just switch the sides to get a on the left side. You can do that if, let's see, if 2 is equal to 1 plus 1, you can switch that and say 1 plus 1 is 2. Same thing here, just with letters. We then divide through by m, both sides. And the m's cancel on the left, and here's our equation. That's 95% of the problem. Now all we have to do is submit our numbers. We have the applied force, 230 newtons, up here. We have the coefficient of friction, 0.30. We have the mass, and we have g. And we divide through by the mass, and we get an acceleration of 2.06 meters per second squared. How far will the box go in 15 seconds? Well, now it's a kinematics problem. We have an initial velocity of 0, and we have an acceleration of 2.06 meters per second squared. We're given time, and we're free to start x0 wherever we want. So we're going to say we start at x0 is equal to 0, And then when we find x, that'll be the distance the box went. So we have 0 plus 0 plus 1/2 the acceleration and time squared. Pretty common error for people to leave out the squared there in the second kinematics equation. Then you get an answer of 232 meters. Now we need the velocity of the box. Well, this time, that's first kinematics equation. We have an initial velocity at 0. We'll assume the box is at rest because we didn't say anything else. We found the acceleration and we know the time. So it's 2.06 meters per second squared times 15 seconds, 30.9 meters per second, and the units work, right? Because you have meters per second squared times seconds, bang, bang, and we have meters per second. Find the kinetic energy of the box. That's just 1/2 mv squared. Plug in our givens and our calculated velocity here, and we get 21,960 joules. How much work is done on the box during the first 15 seconds by the, and we're going to have to wait until the next slide for what the is referring to. But first a break. The equation for work for a force applied over distance d or x or y or whatever variable you want to use is W is equal to Fd. If the object moves in the same direction as the direction of the force, then the work is positive. Work is greater than 0. If the object moves in the direction opposite the direction of the force, then we have negative work. If the object is moving in a direction perpendicular to the direction of the force, then the work is 0. So that will help us with the next few questions. Let's start with the applied force. During the first 15 seconds, the box moves 232 meters. We calculated that. It's in the same direction as the force. It's moving this way. So work is greater than 0. So the force, 230 newtons, times the distance, and we get 53,360 joules. What's the work done by the friction force? Well, in this case, the force is opposite the motion here. So work will be less than 0. So work done by friction is the force of friction times the distance moved. Friction, which we already worked with, is mu times mg. So we plug that in, and here's our mu, here's mass, here's g, here's the distance moved. We get a negative 31,380 joules. So friction is taking energy out of the system here. We'll do the normal force and the gravitational force on the same slide. Why? They're both perpendicular to the distance moved, so the work is 0. So there is 0 work in the y direction. How much work is done on the box during the first 15 seconds by the net force? Well, what is the net force? Well, it's the sum of the work done by the applied force and the friction force in the x direction. And why are we not worried about the y direction? There's no work being done on the y direction, it's perpendicular to the motion. So we have the net force is the applied force plus the friction force. And you're saying, wait, isn't the friction force negative? Yeah, but we're adding the forces up, and the negative will take care of itself on the next line. Here's our net force, 53,360 joules to the right, plus a negative 31,380 joules. Another way of saying that is that's the force to the left. We get a net force in the positive direction, which means we have a net force in the positive direction, which makes sense because we're pushing it in the positive direction and it's moving that way. Compare the work done by the net force and the final kinetic energy. So we're comparing net force to final kinetic energy. Now you may have questioned why we're keeping 4 digits, because I guess the rule we've been using is just have 3. This time I wanted to do 4 because I wanted to compare these at a closer level. The work done by the net force was calculated 21,980 joules. The final kinetic energy was 21,960 joules. Now let's look at our equation here. Initial energy plus net work gives us the final energy. Now what was the initial energy of this box? It wasn't moving. It had no energy, at least no mechanical energy, which is what we're dealing about here. So E0 is equal to 0. So we lose this term, and we get the work done on the system should equal the final kinetic energy. And you might say, wait a minute, it's not exactly equal. I'll go, yeah, that's due to rounding error. We're not going to worry about that at this level of accuracy and precision. So the answer to the question is the work is the same except for slight rounding errors.